Hello everybody, this is ninth lecture on superconductivity and today we are going to study thermal properties. So first property which we are going to study is the entropy. Now when we check the entropy in case of superconductors, we find that the entropy decreases markedly when we cool the superconductors below their critical temperature. Now, what is entropy? Entropy, it is nothing but the measure of the disorder. So, as we are saying that in case of superconductors below critical temperature, entropy decreases, that means disorder decreases. Or in other words, we can say that superconducting state, it is more ordered state than the normal state. And in simple superconductors, if you take the example of type 1 superconductors, there is a spatial order which extends over a distance of 10 raised to minus 6 meter, and that range it is called as coherence length. Now, see here. If you check the entropy for normal conductor, the relationship between entropy and temperature, it is a straight line kind of a thing. Now, here you check the entropy for the superconductors. You can see that it is exponential curve and entropy, it is less. So, superconducting state, it is the ordered state as compared to the normal state. Second property, thermal property which we are going to study today, that is the specific heat. Now, when we talk about the specific heat of the normal metal, it is of the form specific heat, it is given by gamma T plus beta T cube. So, we have two terms in this equation, gamma T, that is the first term, and beta T cube, that is the second term. This first term is in this equation is the specific heat of electrons in the metal, and the second term, it is the contribution of the lattice vibrations at low temperatures. Now, when we talk about the superconductors, we know that in case of superconductors, the temperature is very low. So, lattice vibrations will cease at that low temperature, and that is how the contribution due to the second term, this beta T cube, it will not be there in case of superconductors. So, in case of normal conductors, for specific heat, we have the contribution from the lattice vibrations as well, while in case of superconductors, we don't have the contribution from the lattice vibrations. Now, the number of electrons that are thermally excited along the gap varies exponentially with reciprocal of temperature, and the energy gap is believed to be the characteristic feature of the superconducting state, and this energy gap determines the thermal properties as well as high frequency electromagnetic response of all superconductors. So here you can see that when we take the graph of electron specific heat and temperature. So for superconductors, the graph is exponential kind of here, and for normal one, it is like this. So the nature is very different. Now let us talk about thermal conductivity. Now in metals, like if you take the example of copper, if you increase the electrical conductivity, then there simultaneously there will be increase in the thermal conductivity as well. But the thermal conductivity of the superconducting state of material is not it doesn't change or doesn't increase with respect to the electrical conductivity. In case of superconductors, electrical conductivity is very high, but thermal conductivity is low in comparison with its value in normal state. So why it is so? Here when we talk about low value of thermal conductivity in case of superconductors, this behavior of superconductors we can again explain on the basis of entropy. Now when we talk about superconducting state, it is a highly ordered state, and so there is no disorder to transport and therefore no thermal conductivity. And when we talk about superconductors, thermoelectric effects also disappear. So this is the relationship between superconducting and normal temperature dependence of electronic specific heat in the normal and superconducting states. So that's all about the thermal properties of superconductors. Thank you.